Oh, okay, I think it's working now. Yeah, okay, great. So this is a tutorial. I haven't written a script. Well, now you're seeing all this stuff I've been searching lately. Whatever. We are going to go to this website here, replit.com. Okay. And let's make a new C++ replit. Now we're not actually going to write C++. It's just the closest REPL template for what we want. Now our next job is to install the Verilog compiler to this virtual machine. So you need to go to this show hidden files, and you need to go into this replit.nix. If you edit this file, this is how you can install software to this virtual machine. It's a really good system. Like Replit has become so much better than when I first started using it, like I don't know how long ago. Anyway, so we're going to do packages.verilog. Now, if I edit that and hit enter, okay, so detected change in environment. And now if I type iverilog-version, whoops. Well, anyway, I think it is working. Or maybe -- version. Anyway, whatever, it doesn't matter. So this iVerilog here is Icarus Verilog. This is one of many simulators. Just like how there are different compilers for C++, like G++ or Clang or Circle, there are different simulators for Verilog, and this is a free one. And it's quite good. I've used it before. So anyway, that's what we're using today. It also has the advantage of being very easy to install in Replit. There's another package we're going to need. We're not going to use it right now. We'll use it maybe in about 10 minutes or so. But we're going to need this GTK wave, and we'll see what this is for later. Okay, great. So now let's go into this makefile, and basically we're just going to rewrite this from scratch to be what we want. We're going to make something called, I don't know, let's call it HW for hello world.vvp, which is going to depend on hw.v, and we're going to call this iverilog-o hw.vvp and takes as input hw.v. Actually, maybe let's start by compiling the Verilog and running it on the shell so that you can see what's going on there. So let's just delete all of these old C++ files that we don't want. And let's make a new Verilog file. I'll call it hw.v. Now, Verilog has a lot of very strange idiosyncrasies to it, and well, just take this first hello world thing on faith. You need to make this module, which we'll call, I don't know, I guess I'll call it top end module. And we're going to do initial, begin and end, and $display hello Icarus. Fine. So how do you compile and run Verilog? Unlike, well, it's not unlike C++, but the first thing that you do is you call iVerilog and you give it the path to your file, hw.v. And it makes a.out. Right, I forgot to give it a variable name. Let me just delete this. So just like in G++, you can put -o to select the file name that you want. And we're going to do hw.vvp. So let's take a look at what that did. It generates this bizarre text file that just has a bunch of like stuff in it, okay? This VVP format is specific to Icarus Verilog, okay? Only Icarus Verilog will make this. How do you actually run this file? Like, how do you run this code? You need the other tool that comes with Icarus Verilog called VVP. And this VVP tool, basically it reads a VVP file and runs it. So there we see our hello Icarus statement, okay? Just out of curiosity, I wonder what happens if I don't put that output name. What do we get inside this a.out? We get the exact same thing. So don't get misled by the name here. This is not an executable. You need the special VVP tool to actually run it. Why do we need to compile first to a VVP and only then can we run it? I don't know. There's no reason for it. It's just that's how Icarus Verilog does it. Running Verilog code takes 2 steps. You first compile to this, like, you know, low-level representation, and then you run it. That's just the way it is. I don't know why. Now, this command here, iverilog-o hw.vvp, taking as input hw.v, that's what this is. Now, the other thing we're going to do here is we're going to edit this .replit file. And when you click the run button, basically it'll call this compile. It'll just paste this onto the command line, and then it'll paste this onto the command line. So to compile, we just do that. And to run, we need to do vvp hw.vvp. Okay, fine. So now we can hide the hidden files again and make things look a little bit cleaner. And let's click run, and there, it just works. So now we're ready to write whatever we want inside this hw.v. And then when we run it, it'll just appear on the screen. Let's add another display statement in here, just for fun. Hello to, let's make an, I don't know, this is what I get for not writing a script. I'm trying to think of a good example that's not going to be misleading. Well, let's just run this and convince ourselves that it will run these 2 statements. In Verilog, there are 2 kinds of statements. I guess we'll call it continuous assignments, which we haven't seen yet, and sequential blocks. This initial, begin, end, is an example of a sequential block. There are other types of sequential blocks, which we will see. There's initial, I guess I'll put a lowercase I because that's the syntax you would use. There is always, and there is final. And well, let's just keep going here. So this sequential block, anything that you put in between the begin and end, will be executed like a regular, albeit strange, programming language, in the sense that, you know, here, let's do int x starts at 0. Well, let's not do... so, okay, a second ago I wrote this, which is very similar to something you would write, say, in like C or C++. This does not mean exactly the same thing as it does in C or C++. I'll go into detail about that later, but for now, I'll just not assign it inline. So we can do something like, you know, x equals 7. The format to display is very much like printf in C. So x. Display automatically puts a new line at the end. I actually don't know how to turn that off, so anyway, we'll just keep going. And then we can do x equals 8, and we can do display x equals %d and print out x. Okay, let's hit run and see what happens. Syntax error. Line 11. Invalid module instantiation. Maybe you need to write integer. Oh, okay. Apparently there's a difference between int and integer. Or you know what? I know. Sorry. The keyword in Verilog is integer. There is no keyword int in Verilog. I always forget that. It's just this replit did the syntax highlighting on int for some reason, which made me think that it was the right keyword. But the keyword really is integer. Okay, so hello Icarus, hello 2, x equals 7, x equals 8. So this is, very much like normal programming. Okay. Now let's start doing something which is not like regular programming. What we're going to put here is well, let's do %5, or not percent, but £5 like this. What does this mean? This is a delay statement. So display the simulation time is %t $time, and whoops. And we're going to do this again. And actually, let me also do this. And we'll tag these with the letter A, B, and whoops, C. Click run. So at point A, the simulation time is 0. Fine. It has to start somewhere. Now the thing I wanted to show you here by putting the second simulation time statement is that assignments, or display statements, don't advance the simulation time. But this £5 tells the Verilog simulator, okay, simulate up until time step. What this means is delay 5 from the point where we issued this statement. It doesn't mean go to time 5. So, like for example, if I put another £5 and print out the time again, hit run, time is now 10. Okay, so this means wait 5 units of time. What's the time unit? Well, for now, you can just imagine the time as being an integer, a 64-bit integer. It's just going to start at 0 and tick up with every single delay statement. You can do more complicated things in Verilog, like you can tell it that the time units are like nanoseconds and picoseconds, and you can have fractional time, and we're just not going to do that right now. Okay. Here's where things get interesting. If we put a second initial begin and end, and let's take out this assignment to x here, and let's just reorganize this code a little bit. And let's run it. Okay, well, let's clean this up just a little bit here. And let's also put, just to make things a little bit easier to see on the how do you do this? Initial 1. So this is for initial 1. This is just to help us see what's going on. Initial 2. So this is why the concept of time matters, and this is where things depart from ordinary programming. In Verilog, every statement, so this initial, that initial, I mentioned there are other kinds of sequential blocks like always and final, and I mentioned that there are things called continuous assignments. We haven't seen them yet, but you know, you could write more you know, things here. They all run in parallel. They are understood as if, I mean, the simulator doesn't actually do this because it would be bad for performance and other reasons, but you can imagine that each of these initial blocks and every single always block and every single final block and every single continuous assignment, you can imagine that it is running in its own thread. Fine. So here we have this initial, and both of them start at the same time. So at the beginning here at initial 1A, the simulation time is 0. And initial 2D, the simulation time is 0. Okay? And we see at the beginning that x is equal to 7. You may have a question on your mind, which is the question that, something that we saw earlier. I don't know, let's call this Z, okay. If I run this, we did 1 statement, 2 statement, 3 statements, 4 statements, and yet between A and Z, the time does not advance. That's because the simulation time is not like I don't know how to explain this. I mean, this may not even be a question that you were wondering, but like basically, if these are all threads running at the same time, why is it that multiple statements don't advance the time? And the reason is because, well, man, how do I put this? These statements are sequential, right? This always happens after this, and this always happens after this. There are 2 ways to enforce sequence in Verilog. One of them is to put statements inside a sequential block. This will enforce that they happen one after the other, but the other way is by scheduling things at different times. So if you have statements in the same initial block, or if you have statements in different initial blocks that happen at different times, both of those in different ways will enforce the correct sequence. I hope that makes sense, and I hope I haven't added an extra confusion. I better move on here before I dig a deeper grave. All I'm trying to get at here is that statements inside an initial block will happen in sequence, but they don't advance the time. This delay statement, it's more of like if in a thread you called sleep 5, for example, it basically says, you know, wait for 5 time steps before continuing. Now, the other thing I wanted to draw your attention to here is that, so we have initial A, X, Z, and then after 5 delay ticks, we get to initial 1, B. Simulation time is now 5. X is still 7, it hasn't changed. And then we're going to skip this initial 2 for a second. Take a look at this initial 1c. The simulation time is 10. Fine, that makes sense because we waited another 5 time steps, and now x is equal to 8. And this is quite simply because we have this other initial thread here that waits for 7 ticks. And oh, you'll notice I forgot the semicolon here. It turns out in Verilog, the semicolon after the delay statement is optional. I just like to put it for consistency. I just forgot to put it here, but if I run this again, it does the same thing. So what happened here is that initial 2, the simulation time is 7, right? That's where we got to this initial 2e. And here we wrote the value 8 to x. And that, so in between, so while this one was waiting for 5 ticks, x was overwritten with the value 8. So the next time we printed it out, it has the value 8. Fine. Let's do something a little more interesting. It's time for me to introduce the different data types in Verilog. You know, in C you have int, float, double, right? In Verilog, as you can see, we have this integer x. Actually, in Verilog, integer is actually a, you can think of it as a type def. In reality, in Verilog, we have 2 variable types: wires and reges. I guess I'll just write them as you would write them in Verilog. Now, you may be familiar with digital logic. If you're not familiar with digital logic, ignore the next 10 seconds. Although this is called reg, you may think that means a flip-flop. You may think that means a register. It does not. Okay? These names are misleading. Now, what is the difference between wire and reg? This is the only difference. I'm telling you, you have to believe me. The only difference between wire and reg is that wire, this is for continuous assignments, for left-hand side of continuous assignments. We haven't seen continuous assignments yet. We're going to get there. And reg is for left-hand side of sequential assignments. And we've seen some sequential assignments. Okay. This is a sequential assignment. Why? Because it is an assignment and because it happens inside of a sequential block. Okay. And you can make arrays. So both of these are single bits. Both wire and reg are a single bit. They do not mean wire and register as you might expect. Sometimes in programming languages there's some weird quirk of the language and there is a reason for it, okay? I do not see any reason. I do not know of any reason why you need 2 different variable types depending on how you assign it. I don't know why you need to do this, okay? There's no reason for it as far as I know. Anyway, let's move on here. They are only distinguished by where they are allowed to appear as the left-hand side of an assignment. You can make arrays to have multi-bit, I guess we'll call them signals. So we can do, so wire, you know, W1, W2, etc. This etc. is just, I'm just using this as a variable name. Let's just do W3. You can also do wire. This is how you do arrays. You pronounce this as wire 7 down to 0, W array, okay? This is an 8-bit, I guess, signal, okay? Now, how do you understand this? This is another strange quirk of Verilog, and I don't know why they did this, okay? When you define an array, you give its lowest index, like its lowest valid index that you're allowed to index into, and its highest index. And you use this bizarre syntax here of highest down to lowest to say, basically, we can now access WR0, WR1, WR2, etc., or WR7 as bits. It's just individual bits. Okay. All right. This is an array of 8 wires as wires. Okay. Now, at risk of making things complicated, in Verilog, I don't know why, but in Verilog you are allowed to do something like 0 up to 7. Or you could do 100 up to 107. And those would all make 8-bit signals. In this tutorial, and indeed in pretty much any Verilog you'll ever see someone write in, you know, a real context where they would need to use Verilog for something, they will always do uppermost index down to 0. Okay? Just always do this. The thing is, I don't even know what the difference is. Like, there are subtle and slight and, you know, complicated things that happen if you use like array indices that are not, you know, something down to 0. So just always do this. If you really want to know what the heck is the difference between 0 up to 7 and 7 down to 0, I can't tell you because I don't know. All right, you'll have to look it up in the Verilog standard. But you really don't need anything more than this. I write Verilog at my job. I never need to do anything other than this. Okay? Let's move on. We can have reg, R1, R2, R3, and we can also have reg, 7 down to 0, reg array. Okay? But as I said earlier, the difference between wire and reg is not, I stress, it is not that this represents a wire and this represents a register. No siree, okay? Just forget that this sounds like the word register and that this sounds like the word wire. This just means I can assign to this with a continuous assign, and this means I can assign to this inside of a sequential block. It's the only difference. Fine. Okay, let's take a look at some continuous assignments. Oh, by the way, I mentioned earlier that integer is a shorthand. Well, given that you can put an integer as part of a sequential assignment, as we can see here, this is actually a reg. And an integer is a 32-bit reg. So this is the same as integer 30, this is the same as integer x. Okay, so if I run this, it should have the same results. This is exactly the same as before. Okay. So integer and reg 31 down to 0 are aliases. They're the same thing. Okay, let's look at some continuous assignments. It's very simple. We can do assign w1 equals, oh, I guess I haven't talked about literal values. We're going to talk about it now. What the heck does this mean? this 1 followed by a asterisk, no, not an asterisk, an apostrophe, okay? Let's just write up here. Maybe I'll put this here. Literal values. They have the form number, asterisk, I keep saying asterisk, apostrophe, R for radix, and then you just put your, your numbers here. So, okay, I'll just put n here, and you just put the numbers here. N is the width of the literal, and a number, which can be multiple bits. So a number is the width of the literal. The apostrophe is required Verilog syntax. It just has to be there. R is the radix. It tells Verilog how to interpret blah 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 blah, and blah 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 is the literal value. So R can be B for binary. I think it can be O for octal, but no one ever uses octal. I don't even know why people bother to support it, but anyway. D for decimal. X for hexadecimal. And is that all of them? Yeah. Well, I'm simplifying things here. You can have, there are more radices you can use, but they're just variations on these. We might talk about them like 20 tutorials down the road because they are rather specific and arcane. Okay, fine. Now, here, this is literal of width 1, whose value is 0, interpreted in binary. Assign W2 is equal to 1B1. Blah, 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 blah. So this has value 1. Assign W3 is equal to 1B. Now, hold on to your hat. X. Oh, what does this mean? Well, in Verilog, wires can have value 0, 1, X, or Z. Now, a 0 and a 1 mean exactly what you think they mean. They are just zeros and ones, just like in binary. They're just numbers. Nothing really to say about it. X and Z are special values in Verilog. X means undefined. And Z means undriven. These are basically, for what we're going to be doing, I mean, you don't ever need to use these, but they're part of the language and they're actually useful. How do I put this? In Verilog, there is a difference between a wire, I'll call it unassigned. There is a difference between a wire that has a continuous assignment statement that is assigning its value. And there is well, there's a difference between that and a wire that doesn't have no assignment to W unassigned. I think now is probably a good time to open up the waveform viewer. Well, right before we do that, let me just finish off this example here of continuous assignments. So we can do assign W array equals. Now, this is an 8-bit signal, so we will do a literal of width 8. And let's use hexadecimal. Why not? And we'll do 2b. Oh, x is not the value, it is h. That's my bad. H for hexadecimal. Sorry. 0x2b. Okay. And let's just comment out these regs for now. We'll do them in a second. But let's open up the waveform viewer. So, how do you... Oh, right. I forgot. I forgot how to save VCDs. Shoot. Well, now you're seeing what it's really like to write Verilog. Which is to not know how to do anything and have to look up maybe this. Whatever. This is what GTK wave is, by the way. It's a way to look at waveforms. Whatever. We don't need to do any of this complicated, installing because Replit does all that for us. Replit is awesome. Okay. Yes. You need to do this dump. Oh, man. Okay, I have to apologize here. This is just... Let's just call this required Icarus Verilog trickery to generate a waveform. It is inside of an initial block. Whoops. Again, and we need to do. It's coming back to me now. I remember I did this before. So a dump file. I don't know, thing.vcd. And we're going to use this dump. I think it's called dump limit. So I'm kind of lying to you. When I say that this is Icarus Verilog trickery, actually it isn't specific to Icarus Verilog. This is actually defined in the Verilog standard, that this is how you generate VCDs. It just so happens that most Verilog simulators will just make a waveform for you if you give it like a command line argument. You don't have to actually write this in your Verilog to get a VCD, but in Icarus Verilog you do. Fine. So IEEE 1364 standard. So this is something that you will probably, if you're serious about writing Verilog, you will have no choice but to look at this standard all the time. It's not unlike C++ where you're constantly going to be browsing CPP reference, wondering, what the heck a certain thing does or how to do a certain thing. Luckily for us, the Verilog standard is really, really good. It's really good, okay? It's well organized. It has a great index. All the links in the PDF are clickable. There are nice examples for everything. So actually, it's a 600-page standard here. I haven't read it cover to cover, but it explains all the intricacies that you need. I have never had a situation, never once, where I was unsure about something and the standard did not answer my question. I have always found the answer in the standard. It's very, very good. I cannot say the same thing for the other IEEE standards. Sometimes they're miserably difficult to read, but this one is okay. All right, where's VCDs? Yeah, so the Verilog standard defines this file format called VCD, which stands for Value Change Dump. Well, I don't know what else to say. It's the file format for saving a waveform of what happened in your Verilog. So anyway, specifying name of dump file. So we did that, thing.vcd. Specifying variables to be dumped. We want to dump everything, and there's a special way to do that, but I forget what it does. The dump virus task. When invoked with no arguments, dump virus dumps all the variables. Okay, great. That's what we want. Dump virus. Give me everything. Now, there is one downside to using Replit. Although it seems they may have fixed it. This bar here at the bottom that shows you the CPU, RAM, and storage, that's new as of, I don't know, a few months ago. The last time I did something on Replit, I mean, where I needed a lot of storage, I accidentally filled up the storage and didn't realize, and it crashed Replit, and it was really difficult to recover that project. So actually, that may be fixed, but anyway, we want to be careful about not filling out the space. I actually don't know how much space I have. 1024. I'm going to assume that is kilobytes. So there's this other, I forget what it is. No, we don't want this dump on, dump off, dump all. No, we don't want that. Dump limit, this is what I want. The dump limit task can be used to set the size of the VCD file. I think it's in bytes, so dump limit 512 KB. This is not necessary. You could leave it out, but this is just to prevent me from overflowing the storage I'm allowed to use in Replit. Okay, so let's run this. Great, we get a thing.vcd. It is, well, I wouldn't necessarily call it human readable, but it is an ASCII, which means there's, you could look at this, but anyway. I want to look at this in an actual waveform viewer. Now, earlier, inside replit.nix, we asked it to install a GTK wave. Now, if you haven't seen Replit before, this is going to blow your mind, okay? GTK wave thing.vcd, and actually there's an argument to GTK wave -a. I think it's -A. The -A will make it so that if we edit those signals that we display in the waveform, they will save command line options, page 63. Whoops. Yeah, it is -A. So autosave name. Basically, this will prevent us from having to, well, just do it, okay? Now, amazingly, all right, Replit never ceases to amaze me. As a standard feature, okay, all of the virtual machines have a VNC server. Okay, so this Replit is actually a virtual machine, and this web page that you're seeing here has a JavaScript VNC client that is drawing to this HTML canvas right here, and that is how on any Replit you can have a desktop environment, which is so amazing. It's just amazing that this even works, and it's so smooth and it works flawlessly. Well, maybe not completely flawlessly, because like some of the icons aren't loading. I don't really know why. We could try to fix that. There's probably a package I need. GTK Live icons not showing. Well, forget it. I don't want to waste time with that. Now, you'll notice here that we just don't see anything. That is because we need to add signals to the viewer. This is what I mean by having an autosave. A lot of time when you're writing Verilog and debugging it, you spend a lot of time like customizing your waveform viewer to show things in a particular way, and it takes a lot of time and effort to set up your waveform viewer, and you really don't want to redo it every single time. So the way this works is this here, I don't know what SST stands for, but this SST is showing you your modules. So notice here that this top matches this module top that we called it here. Let's start by putting X inside the waveform. Now one of these buttons resizes zoom fit. So X is a 31 element reg. It starts off with the value 7, and at time 7, right, you see here, marker 7 seconds. Okay, you see that? At time 7, it gets assigned the value 8. Okay. Now, continuous assignment statements, let's start with wire 1. Well, it just has the value 0. You'll actually notice, I don't know if you can see that, but how do you zoom in here? Zoom in. Actually, it might just be a GTK glitch. I thought I saw that maybe at the start there was a little glitch, but oh yeah, you see, I don't know if you can see that little green line there. GTK, I think by default starts off signals at 1, but then at time 0, because the simulation always starts at time 0, we assign it to 0. So anyway, ignore any glitches at time 0 in the waveform viewer. They don't mean anything. It's just a quirk of GTK wave. Okay, fine. So if we pull up wire 2, we will see that it is always 1. Okay, that's encouraging. And if I pull up wire 3, we'll see that it is X. This is how GTK represents X, just a red bar. X is a special signal in Verilog. It means undefined. It is used for errors, or you can use it yourself to basically mean I don't know, like treat this wire as an error wire or something. It's not common actually to assign X in your own code. Usually when you get X's, it's because, well, I'll show you an example of something that makes X's in a second. For now, let's just keep looking at the signals. So if we open up this W array, it has the value 2B. Great, fine, okay. Now I just hit Control S on my keyboard, and you'll notice it saved this thing.gtkw. This is the description of, oh geez, I don't want to be doing that. This is the description of the signals I have on here. So like if I change the order or moved different signals on, or you can also change the radix of the representation here. So this is now being represented in decimal, 2B is 43 in decimal. We could change this to binary, and here we see the 32 bits of it. All of these things, if I hit Control S, you'll see that this well, I don't know exactly, but anyway, this save file here will remember how I configured the waveform viewer. All right, enough babbling. Let's move on. Let's start talking about sequential assignments. Okay. So let's do always blocks. Now, the format of an always block is always at sensitivity list begin statements. And what is this sensitivity list? It's hard to explain. Okay, remember earlier that we said any sequence of statements that doesn't include a delay block happens in 0 time. They happen in order, but they happen in 0 time. This is what I get for not writing a script. This is what I get for not writing a script. Basically, the way to understand always blocks, for now, I'm just going to write this always at star. Okay. Now, this isn't actually a placeholder. This is actually valid Verilog. Normally, in a sensitivity list, you would write variables in here. So I could write like R1, R2, or whatever I wanted. Okay. Star means be sensitive to everything, kind of. Basically, this always block, the difference between always blocks and initial blocks are triggered. In other words, they begin executing at time 0. That's why they're called initial. Always blocks will begin executing every time something in their sensitivity list changes. Okay? You know what? Let's put X in here just to show you. Now, let's start by initializing these registers. Okay, initial. So, at time 0, give a value to the registers. R1 equals 1B0, R2 equals 1, let's just make them all 0, B0, R3 equals 1B0, and RR equals 8B0, okay? And here's what we're gonna do. Always at X, which is a strange thing to do, but you'll see. We will do RARR is equal to, let's do RARR plus 8B1. So every time X changes, this always block will be triggered and it will increment RARR by 1. Now let's just run it. Okay, fine. And now let's do GTK wave. I don't know why GTK wave was killed just there, but it's fine because we saved our signals. Oh, and we need the dash capital A. Okay, because we used dash capital A, it automatically reloaded our save file, so it put all our signals back. All right, let's put in our new signals. R1, R2, R3, and RR. Oh, I don't want them there, I want them down here. So, R1, R2, and R3 are assigned the value 0 at the beginning, and we never assign new values to them, so it makes sense that they stay at 0 forever. This is something interesting. RARR starts at, it appears to start at 1. What's going on? Well, every time X changes, this always block is triggered. And it changed here. We assigned it the value 7 at time 0. So, oh, you know what? You know what I should really do? Display always 1 triggered at time %t. And always 1. So now if I run this, always 1 triggered at time 0. Man, I don't know why there's so many like spaces here. I think you can put %0t. I think you can put 0 like this, kind of like in printf where you're specifying the width. In fact, it's exactly like printf where you specify the width. And this will get rid of the extra spaces that are making this so hard to read. Okay, there we go. Always 1 triggered at time 0. Therefore, at time 0, where is that? Always 1. At time 0, we took our array and incremented it by 1. And then always 1 triggered at time 7. Why? Well, because X was changed at time 7. Therefore, the sensitivity list said, aha, I need to kick off another one of these always blocks. Okay. Well, that's pretty much all I wanted to talk about in this first tutorial. Let's recap. I guess let's put it at the bottom. Edit replit.nix to say packages.verilog and packages.gtkwave. Edit makefile. Oh, you need to click the show hidden files. Or actually, even before that, make a C++ REPL show hidden files. And so edit the makefile, well, you know, to say that, basically. I mean, you can edit this makefile to say whatever you want, but, you know, edit makefile to invoke iVerilog, edit.replit run statement to invoke VVP. This right here. We didn't need to do that, but it was just, you know, it was nice to be able to click this nice green run button and have it make and run instead of having to do it on the command line every time, you know. Okay. And then basically we talked about continuous assignments, sequential assignments, within sequential assignments, always blocks triggered whenever sensitivity list changes, initial blocks triggered at time 0. I didn't talk about them, but there's final blocks, which, you know, are triggered at the end of the simulation. We talked about wire versus reg, and we talked about literals. Yeah, I better stop this. It's probably like an hour long already. Yeah, almost exactly an hour. Okay.